Our next speaker is Gianluca Curzi. We will be speaking on computational aspects of cyclic and
thanks. So this is the last of the session. We'll assume the audience is now familiar with the basic notion of cyclic proof and non-wellfounded proof, and we'll go straight to the point. So this talk is about the computational analysis of cyclic and non-wellfounded proofs, and I will focus on my personal contribution on the topic, which is the outcome of a series of joint works we done with us in this book. In particular, I want to tell you about two directions of my research, in particular in each book. The first one is the computational strength of logics with least and greatest points. And the second one is about the complexity theoretical aspects of cyclic proofs. And the overarching idea here is that we want to consider cyclic proofs as computational objects, as programs, and we want to extract some recursion mechanism out of it. Some motivation. So why are we interested in this topic? Well, because we don't know much about the computational aspects of cyclic proofs in the first place. But also, when we reason about cyclic and non-wellfounded proofs, very often we run across very interesting reasoning principles, such as the pigeonhole principle, Phoenix lemma, and interesting proof methods, such as bisimulation and related functions. Finally, cyclic proofs introduce very complex and intertwined loop structures. So computationally, they are very interesting objects. And it's very difficult to extract recursion mechanisms out of cyclic proofs. This is what is making this topic very interesting from the viewpoint of computation. Some preliminary wording. So this is a conference on mathematical foundations of programming language, programming semantics, and there is very little about programming and nothing about semantics. So apologies for that. Secondly, this is a very quick overview, so if you're interested in the topic, just ask me questions. I'm very happy to provide details. And last, this is a propaganda talk because I'm trying to convince you that cyclic proofs are really nice objects. So cyclic proof theory is fun, come join us. So, fixed point logics. So, why fixed point logics in the first place? Well, because fixed points are pervasive in mathematics and computer science. From a logical viewpoint, we use fixed points to model inductive and co-inductive reasoning, and from a computational viewpoint, we use fixed point logics to represent express recursion mechanisms and co-recursion mechanisms. So very powerful tools. We are particularly interested in those fixed point logics having a constructive content. So we will consider proof systems as type systems. We want to see cyclic proofs as programs, and we will be considering both the traditional inductive unitary proof systems for the fixed point logics, and also their cyclic proof theoretic counterparts. And we will be focusing on intuitionistic logic with least and greatest fixed point operators, so mu-Lj. But the results of this part of the talk will apply to many other logics with fixed point logics with a constructive content, such as mu-Mul and mu-Ll. As I've mentioned, it's very first talk of this session. So the fundamental question of this part of the talk is the following: what class of functions and natural numbers do proof systems with fixed points represent, both in their planetary version and in their cyclic proof theoretic version? So on the result, the main result, all of these fixed point logics represent the same class of functions, namely those probably recursive, probably totally the subsystem of second order arithmetic I want to say zero. So first we define the inductive version of MuLJ. So the formulas are rules of impressionistic logic. So we have propositional variables, units, implication, conjunction, disjunction. And also we extend the grammar with least negative fixed point operators along with this side condition, which says that x occurs positively in sigma. Just to recall you the notion of positivity in this case. So when we have a variable, the propositional variable occurring on the left-hand side in the antecedent of multiplication, then this occurs negatively. The multiplication flips polarity. So this is not a formula of MuLJ. For the same reasoning, this is a formula of MuLJ because x occurs on the right-hand side of the multiplication. And what about the last example? When I say positively, I mean hereditarily positively. So x occurs negatively in this formula, which occurs in turn negatively in the output formula. So this is, in fact, the formula of MuLJ. What about the inference rules given in signal calculus presentation? Well, we extend those for MuLJ with the following four rules for mu and mu, so for the least and the greatest point. The first one says that mu is a prefix point. The second one says that it is the of all the prefix points. So we basically apply the Nast's theorem, characterizing mu as a least fixed point. And dually for the greatest fixed point operator. So post-fixed point and join of all the post-fixed points. What about the cyclic theoretic version of MuLJ? So CMuLJ. Formulas are the same. What we change is the set of inference rules. So notice that these rules are a bit more symmetric with respect to the previous ones for MuLJ, because they allow us to unfold or fold depending on the way these rules. Both from the right-hand side of the implication, the turnstile, and on the left-hand side. Okay, so they are perfectly symmetric. And also notice that the rules for mu and the rules for nu are precisely the same. So there is no way of discriminating the behavior of mu and nu. So how do we go about it? Well, as Azad anticipated, we consider non-wellfounded proofs generated from this set of inference rules, and we apply the validity condition for progressivity, which basically roughly says that the proof is a good proof if for any infinite branch there is like a subformula path where somehow the greatest fixed point on the right-hand side of the turnstile or the least fixed point on the left-hand side of the turnstile unfolds infinitely many times, so that we are asymmetrizing the behavior of mu and the behavior of mu. Having this definition in mind, I can define what the cyclic proof sequence CMuLJ is. And this is basically the set of non-wellfounded proofs that satisfy the regularity condition, so the underlying infinitary tree-like structure is regular. And this allows us to see the proofs as cyclic proofs, so finite proof trees with backlinks. And then the progressivity condition I just mentioned, which as a byproduct guarantees the logical. Now, we can represent functions and natural numbers in both the finitary and the cyclic proof theoretic version of MuLJ. In particular, natural numbers, as I've mentioned, can be encoded by the following type of formula, which is basically the least solution of equation 1 plus x equals x. So we can encode the natural number n using basically n plus 1 units. It's quite like the Italian notation for a natural number. So that we can encode so cyclic and inductive proofs can be used to represent functions with natural numbers. And here we use cat elimination to model computation. Okay, so proof rewriting is quite like program rewriting. Now, concrete example, addition, the recursive definition of addition can be encoded in ULJ, so in the inductive system as follows. So we have two formulas in the context, two types n. The first one corresponds to the recursive parameter and the other one to the side parameter. So basically this proof can be seen as a program that first analyzes n, so it unfolds n, because n is a fixed point, and then it analyzes basically the input. If it is 0, then there is just one unit. And so we switch to the base case and we select the safety side parameter. If it is strictly greater than 1, than 0, then we basically apply the recursive call, which is not visible in this program, and we apply the successor to it, decreasing by 1 the recursive parameter, which is basically the second declaration of the recursive definition of addition. So we cannot see easily the recursive call here and how the program works, but something better happens in the cyclic, the theoretic version of ULJ, where we can basically mimic the recursive code using backlinks. Okay, so the program, the behavior, the computational behavior of the program is visible right from the definition. We can encode strings or other conductive data as well. For instance, strings of natural numbers can be encoded by non-wellfounded, possibly non-cyclic tree, essentially because we cannot describe strings of natural numbers without things. Here, the type S is the type that can be seen as the greatest fixed point, and it can be seen as the solution of the equation n times x equals x, where n is the type of natural number. What is the takeaway here? So CMULJ can be seen as a set of non-wellfounded proofs satisfying two conditions, regularity and progressivity. Regularity is finite presentability of a non-wellfounded proof. So it corresponds from the viewpoint of computation to uniformity. What about progressivity, which ensures logical consistency? Well, from the viewpoint of computation is a totality condition. Let us consider this example. We have one infinite branch in the non-wellfounded proof, one unique link, and along this infinite branch we have this subformula path, the one tracing the recursive parameter, and this basically unfolds infinitely many times, and it decreases by one parameter. So somehow this ensures, so this proof is progressing because by virtue of this like reasoning, and the recursive parameter basically decreases sufficiently many times to reach 0 eventually. So we eventually escape and we reach the base case. And that this is the recursion theoretic reading of a cyclic proof. So this is how we extract recursion of a cyclic proof satisfying. Now, to establish our results, we need two theories of arithmetic. The first one is MFPS, which is basically the extension of PA with least fixed point operators. We have basically the same formulas of PA, but we add set variables, so membership of a term with respect to set variable, and membership of a term with respect to the least fixed point formula, along with the usual positivity condition. The theory, MFPA, is basically the extension of PA by the following axioms that basically say that mu x, little x, phi is a prefix point equal to the least of all the least. It's a least fixed point. What about phi 1 to CA0? This is roughly a subsystem of second-order arithmetic where the comprehension scheme, which is a set existence, axiom saying that there is set for any formula that specifies the extension of formula is restricted to pi1 formulas. These are basically formulas described in terms of second order universal quantifier followed by second order existential followed by an arithmetic. And interestingly enough, these two theories are correlated by a nice result by Müller-Field in 2002, which says that pi1 to C0 is arithmetically conservative. They could be totality the same functions. And so the fundamental theorem of this first part of the talk is the following: neo J and C-neo J, many other constructive logics by extending the log, represent the same class of functions, namely those provably recursive in C0. The theories are sketched to prove. So we start from a simulation result, which is basically a translation from iterators and coiterators defined here to cyclic construction. And as a result, any function representable here is representable. Then one of the two most interesting bits of this proof is that, so remember that with any function, so functions are representable here, but we said that furthermore, any function representable is total because of velocity. So we have to prove this by a means of a totality argument that requires that is based on a hereditary reciprocity argument. So we can prove that any function representable here is total, and what is more, we can formalize mathematically the hereditary argument in terms of pi1 to C0, which means that basically the functions representable here are provably total. And then we rely on Müller-Field result. So any function probably recursive here, probably recursive here, and finally we conclude by a realizability argument, saying that basically any function probably recursive here is representable here. So we are relating the representable functions of systems with probably recursive functions. Theories of Let's move on to the second part of the talk, which is devoted to cyclic implicit complexity. So let me just define what implicit computational complexity is again. It can be seen as a branch of computational complexity that aims at characterizing complexity classes without explicit reference to machine models, in particular reducible systems, like systems, functional algebras, and so on, not machine models. And we don't want to have this systems with some explicit resource bounds. So complexity classes are defined on top of resource bounds, and there is resource bound, but we want our calculi to capture the inherent principles of computation, bounded computation, without explicitly mentioning bound. And the purpose is notion here. Implicit computational complexity is the notion of stratification. So we stratify data, we organize data into layers, and so computation is performed layer by layer, and this induces a bound computation. This is roughly how we capture complexity classes in the spirit of implicit computation. And we will see sacred version as an example, a concrete example of how stratification works. So what is cyclic implicit complexity? This is like basically a branch of the cyclic theory I introduced in joint work with Lunas and other ongoing collaborations on the topic. And this basically aims at characterizing complexity classes in the spirit of implicit computational complexity, but using the principles of cyclic and non-wellfounded theory. So basically, quite like the progressivity condition, we will apply global criteria to this to get rid of the cyclic proofs that overstep like some computational bounds, so that we can induce a bound computation. So safe recursion is an instance of implicit computational complexity based function algebra. So this is an algebra of functions could be with a mountain proof, and it is based on the notion of safe recursion notation. So in this function algebra, the function arguments are partitioned formal parameters, the red ones, and safe parameters, the green ones. Why is that? Well, because we want to implement a restricted version of recursion called safe recursion. I will gloss over the notation part of safe recursion notation to give you just the basic idea behind it. So with safe recursion, the recursive parameters are always the red ones, the normal ones, and the recursive poles are the green ones, always placed in safe position, so that it is never the case that the recursive pole of the function we are defining is in turn the recursive parameter of the previously defined function h. And this induces a bound like a stratification, so we stratify it that we never mix up recursive poles, and this induces the polynomial bound. Also, safe composition is a variant of composition that allows us to preserve the safe non-distinction arguments. As a result, the resulting function algebra characterizes the class of functions in polynomial time. And we will try to find a circular version of this function algebra, but in a proof-theoretic fashion. First of all, recall the way we represent recursion using cyclic proofs. So we have some form of case analysis on the recursive parameter, and then we have a base case represented by a cyclic proof, the step case represented by a cyclic proof where we compose using one of its parameters, the recursive. Now, how do we turn this recursion theoretically into safe recursion? Well, an idea can be to add a modality, so that modal formulas correspond to normal parameters. The normal formulas correspond to safe parameters, and we add some global proprietary conditions similar to recidivity that enforce this distinction and gets rid of all the non-safe recursion schemes definable in our cyclic theoretic setting. So, for instance, this is how safe recursion would look like in our system, where the recursive parameter is now corresponds to the model form. Unfortunately, it's not that easy to get rid of all the non-safe instances of recursion. We need several global conditions, and in particular, I just want to draw your attention to a very interesting case that arises in the cyclic system, where we have just the modal-non-modal distinction, but without global conditions. So we can define an example, so nested safe recursion. So this is a safe recursion because it's in safe position, but it's nesting the recursive on another recursive. Okay, and nested recursion allows us to define exponential functions. So if you want to characterize the polynomial time, we have to get rid of structures like this. And notice that from the cyclic theoretic side of the story, we are nesting somehow loops. We are creating more complex loop structures that we would like to get rid of. Interestingly enough, this is a nested safe recursion, and nested recursion in general is like a recurring pattern in the literature. For instance, when we try to have to lift safe recursion to a higher order setting, that's what one did. Sorry. we have to impose some condition that prevents nested recursion from happening, because basically this nesting is very, like, it has a very higher feature. In a way, our global conditions will mimic this linearity condition on higher safe recursion. Basically, what we want to do from the recursion theoretic side is that we want to prevent application of higher functions so that we can never nest two copies of the one inside the other. So we can define a cyclic theoretic version of the functional over B called CB, which collects non-wellfounded proofs generated by a set of inference proofs that I haven't presented, and that satisfy the following requirements. So we have regularity condition, which gives us uniformity. Progressivity gives us totality, as I mentioned before. And then we have safety condition, which is a global condition that allows us to maintain the safe distinction of an infinitary setting, in an infinitary setting at a global level. And then we have the left-leaning condition, which is a linearity condition. This is precisely the one discarding nested safe recursion. And as a result, we can prove that all the functions representable in our cyclic proof system are precisely proofs. We don't have time, and interestingly enough, if we draw the left linearity condition, which the left-leaning condition, linearity condition, we get precisely the class of elementary functions. So we can extend these results to capture the uniform version of the class of functions computable in a uniform polynomial line. What does it mean? Well, there are many ways of characterizing this class. We can define FD poly class as a set of functions that can be computed by polynomial-sized circuits, but there is another alternative characterization of this class that is more useful to us for establishing our characterization. FD poly can be seen alternatively as the class of functions computed in polynomial time by a standard deterministic Turing machine that can query bits from real numbers. Okay, so we will call it FD relative to oracles, real numbers. Now, how do we get a characterization of FD poly starting from our characterization of FD? Well, the idea, as I told you, is that regularity condition is a uniformity condition combination. So if we want to characterize the uniform version of FP, we need to relax regularity. So we will have a weaker version of regularity, which allows us to express computability with respect to computability plus querying bits of real numbers. And since FD poly is equal to real numbers, then we basically characterize our non-uniform polynomial time. So in the end, we can by relaxing the regularity condition CD, we get a non-wellfounded system that characterizes FD poly. I just give you the idea of the proof. Well, by weakening regularity, we can decompose a non-wellfounded proof that can be derived from the system as follows. There is a cyclic part that corresponds roughly to the cyclic proof within CD, so the cyclic proof system characterized in P. And then there is a fully fledged non-wellfounded part, the non-cyclic part, which somehow represents a series of real numbers from which we query these. So somehow a proof of our non-wellfounded system can be decomposed into a cyclic proof in CP plus some non-wellfounded proofs that represent oracles. And this is basically equivalent to FP relativized to R, and the proof is basically lifting the characterization of FP given CV to real numbers in Oracle, and then we diverge on the equivalence and FP only to get our result. So somehow we have a decomposition result thanks to weak regularity that allows us to analyze this. So conclusions. So wrapping up, we have identified computational proximity of two binary and cyclic fixed-point logics. We have introduced good methods for investigating the computational complexity in the sector of cyclic and non-wellfounded. There are like a series of future and ongoing works I want to tell you about. The first one is an ongoing work with Lucas Langer. We are trying to establish an equivalence between UPA, the theory that I mentioned before, with its cyclic version, and this result somehow generalizes the previous result by Das and Langer about the theory of ID less than omega. As a future work, it would be really interesting to restrict μLJ and CμLJ to strictly positive fixed points to see if the equivalence in these two systems still is. Strictly positive means that we never bind variables under the left of an implication. Concerning the second part, we have a fresh result in joint work with Matteo Flavio Guglielmi, where we apply cyclic complexity in the setting of linear logic. In particular, we consider a subsystem of linear logic we call parsimonious linear logic, inspired by parsimonious logic, which is actually a type system of logic introduced by and we characterize the same functions, FP and FP. As a future work in the setting of cyclic complexity, it would be nice to extend this topic to space complexity and lift our system to understand higher level question. And this is it. Thank you.
I didn't hear very much what they said. What is semantics?
Oh, yeah.
Just didn't hear, so it's not a wrong question.
Yeah. So it's so parsimonious logic is a variant of linear logic where the is it's like A, and you have like streams or data like that. So that so that you have two inference rules that can be seen as being the diffusion of operation for streams. And this is not a subsystem proper subsystem of linear logic. We explored a fragment of parsimonious logic that can be seen as a proper subsystem of linear logic, where you still preserve these computational results with respect to this this subsystem of linear logic, which parsimonious linear logic inspired by parsimony.
So, in the first part of your book, translation from arithmetic is from provably total functions, you have to the left edge here, and the arithmetic fixed point ULJ,
Yes.
based on a realized guide. And the result looks kind of analogous to, for example, Girard's translation of, say, sectional arithmetic.
Yes.
So is that analogy correct? And in what sense does that realizability argument?
It is indeed an instantiation, somehow an instantiation that realizability. So we consider we define our realizability notion of our realizability using the second order encoding of these points. So it's precisely there are like some technical aspects that I think the problem was about commutation, commuting realizability with modifiers, and, but more or less the spirit is the same.
Wondering only effects. Can you give us a realizability argument in your technical complexity with realizability effects in like sub-theories like algorithm?
That's a very interesting question.
You need a cyclic predicate theory to interpret this. Because the realizability argument you have, you get a term. You also get a verification, and both these things will have structure like the original in the realized. That's kind of like theory, the cyclic both in the term part and in the.
Can you hear me, Abhishek? Can you hear me?